will be an e to the minus I n minus m after speaking. And if you leave t running for long enough,
Expect for 3 hours.
when it does it, n doesn't.
Sorry,
Cool guitar.
So, for those of you who weren't there at the tutorial, probably won't understand what's going on. But let's just put it that you asked for this. Oh. Come in, Damon.
Yeah, made it.
You made it. Well, what did you make it to?
Is this camera set up?
Today is gonna be the day that we follow Alice down the hole. Turns out humans a pill that you're better off swallowing whole. And I don't believe that anybody feels comfortable with what they know. Measurement as a postulate is bent, because predictions needed well defined. Appearance goes with collapse in one big jump, so we need to know when it is time. And I don't believe that anybody collapses quantum states with their mind. And all my thoughts and feelings seem quite classical. By that I mean they seem to be single value. There are many things that I'd like to say to you, and I know just how. So to start today, got a game to play to help you feel quantum mechanics is real. So seriously, we're going to play this game. Okay, so arrange your chairs, form into pairs. You're going to lose. Seriously.
Probably.
Then be hard. Interrogate.
Well, it's palms up.
I'm smarted.
Alright.
So just to be clear, you are actually forming up in pairs now. It can't all be me singing, right? That's not fair.
Yes, we can.
Have you ever been to a concert?
There's a lot of songs in this set, right? There's a lot of stuff that you need to.
For quantum mechanics, the musical.
So in pairs, you're going to do some conclusions now. You're going to come up with a plan.
Over in this room.
And then after that, you're going to be separated causally. And you're going to be asked a lot of different questions. Okay? Your answers must follow these rules. You're going to be asked 2 kinds of questions. What kind of food and what is your favorite color? It's always got to be green or red. Peas or carrots, and your answers must be correlated in this way. Cool. Do people understand the game?
Yes.
So you're not allowed to communicate once you're separated. Okay? You don't know what your friend's going to be asked in their room. It's like a prisoner's dilemma. You know, you have to make sure that you agree in this particular way without trying to cheat. And it can be done. Go nuts.
Can you click back to the...
Were you allowed to share a personal table system?
Maybe.
Okay.
So EPR was saying that we should be able to do this kind of collusion, right? This is a thing that entangled states can do, yes. But if when you separate pairs of particles, they can still, when you separate them enough, they should have everything you need to know with them. Okay? And so you guys together, you're going to be separated. You should be able to have everything you need to know to act like quantum particles. Okay? This is the simplest system we can have, 2 states. Does anyone have any kind of pitches for doing it classically?
You don't have all the information because you don't know what question they're asking.
You don't know what question they're going to ask you. But on the other hand, how can the separated particles possibly know either? The quantum ones. How can they possibly know what the other one's being asked? Right? That's a fair question. That's basically the question Einstein was asking. Okay? Okay, so what happens is you can't do it by prior agreement classically. And the easy way to look at that, sometimes you have to both answer green. Let's just look at those subset of cases. Right, so we ignore all other things that you're trying to do. So look at the times when you would have both said green. So if you're asked the colour at that time, you'll say green. And so therefore, if you're asked food, you know the other guy is going to be saying green if they're asked colour. So you have to say peas, or you might accidentally violate that. So if you're both asked food, you both have to say peas. Right, so it's a quarter of the time on the cases where you would have had green, green, you'll accidentally say peas, peas. You can, of course, do it quantum mechanically. So sharing entangled objects. So here is a state that'll work. Right? So we've got peas and carrots, and green and red are our 2 pairs of basis states. So we've got carrot and peas, peas and carrots, minus carrots and carrots. So we've got this. Just check that obeys the rules of the game. And then you can get the probability that they actually both say green. It's a quick change of basis. I'll save you some time. Note that it's symmetric between the 2 of them. So you only have to do it one way, you don't have to check both ways. It's quite important that you are able to rapidly change basis on tensor product states, which is one of the reasons why I'm doing that there. Another thing is to make you feel yes. There are things I can do with a pair of entangled particles that I cannot do by collusion. Does that annoy you, surprise you, bore you? You've seen it before. What does it mean?
It means it's strong evidence of quantum mechanics.
It's strong evidence for quantum mechanics, but we don't even really know what quantum mechanics is yet because we don't know what that. Can you check that's still pointing around?
Yeah.
We don't know.
Yep.
Thank you. We don't know what a measurement is. We don't know how this wave function collapse thing works. Right? And in fact, the whole EPR setup was basically supposed to say, look, it would be stupid if quantum mechanics worked this way, therefore it can't be the whole story. And now we've kind of shown that there isn't much of a story underneath it. Those wave functions are about as real as you're going to get, right? Because they are required. So we need to describe this wave function collapse. So quantum mechanics really seems unlogical with crazy waves collapsing when you look at them. They're not secret particles, I can't see how it's causal and I don't even know how to predict the jumps. Do 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 do. Do 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 do. Don't you remember rules of Schrodinger? Everything is linear at the micro scale. But if you model measurement, you'll end up with entanglement. Nothing ever true, the tree is just one branch. Do 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 do. Getting nervous at the mesoscale, at the mesoscale, at the mesoscale. Getting nervous at the mesoscale, at the mesoscale, at the mesoscale. Why? Why do we get nervous at the mesoscale? That's between micro and macro. It's in between the grey area.
We don't know whether wave function should collapse.
We don't know whether wave functions should collapse, right? And by we, of course, I mean the experimentalists, right, in the room, are building things to make large quantum entanglement right now, for purposes, for reasons. Okay, we need to know whether those wave functions are collapsing or not. We need to know when. Currently, the third postulate says when you look at things, wave functions collapse. Well, what does looking mean? What does that mean? And it seems kind of odd that it would involve anything like actual looking. And when this goes into the public domain, it tends to look like, oh, magic, secrets, people are magic. And it doesn't necessarily have to be that way, you see?
I think it is.
Come on, Ethan, you're on. No, you're a drumming member.
Oh, no.
Hey, someone drumming. All right, you guys have to drum with me. Something special in the chain, trimming entanglement, explaining this world. Something special in the chain, trimming entanglement, explaining this world. It's not in electrons or atoms, photons or quarks. Think about that. It's not in. It's not in electrons or atoms, photons or quarks, but it's something in us. Is consciousness the key? A classical field that stops the spinning entangle. Is consciousness the key? A classical field that stops the spinning entangle. Alrighty, let's think about that.
I feel you're driving at something. I get that.
You get that feeling?
I can't
Alright,
watch.
next one.
Joe just starting a cult about this. No. Jam plug.
So,
I was just searching.
there's a reason why
to get a guitar.
Schrodinger used the cat example. Why did Schrodinger use the cat example to talk about quantum mechanics? Okay. It's not because he hated cats.
He lived with cats.
Although, I must say, try and get the Schrodinger's cat experiment through ethics approval is hell. Okay.
Didn't he?
So we've got a beam splitter with a cat, and if the photon goes one way through the beam splitter, what a photon actually does is it goes both ways through a beam splitter, right? It goes through that plus, with a pi phase change, it goes through that way. Pi on 2 phase change, it goes that way, right? If this detector goes click, some sleeping gas is released, right? And otherwise it's not. So what we have here, we have a superposition. We have a superposition of photons going that way, right? If we go back to the chain, we have the chain pictures. Okay. If we have a superposition of photons, then we end up with a superposition of our detector going click and no click. And then we have a superposition of our cat being active and dormant. Okay. So here we have a picture of an active and a dormant cat. Okay. What happens if you open the box? Why did Schrodinger use this example?
Because the question is, can the cat measure itself?
That we're going there. Schrodinger used this example as a kind of absurd example. He thought it was obviously stupid that a cat could be active plus dormant. Right? He thought it was, a cat can obviously only be active or dormant. What's the difference? No. What's the difference between active plus dormant or active or dormant?
One's awake,
Nope. So what would the measurement postulate tell you you'd get if you open this box?
one or the other.
One or the other. That's active or dormant. Right? What does quantum mechanics tell you is in the box?
Both.
Right? Plus, with a particular phase relationship. That phase relationship is still in there somewhere. It's probably hideously complicated by now, but it's still in there somewhere. All right? Now, Schrodinger didn't believe the measurement postulate. He didn't believe the quantum jumps. He famously said that if they're not taking me out for the theory at some point, you know, I wash my hands of the whole thing. Okay, and so he used this example, this thought example, so look, obviously you can't have an alive plus a dead cat, all right, or an active plus a dormant cat, as the case may be. All right?
I know you've seen cats.
How I seen cats. Well, they're mainly dormant, right? Okay, so what happens if you open the box? Answer that question. You get a cat scratching your face, or you get a cat not scratching your face. All right. So our posture would say, our rule of thumb posture says you collapse the wave function, you have one or the other. Suddenly the wave function changes, and this plus goes away. Yeah. Could you write the density matrix for what you expect to see? Hands up if you could. All right. The rest of you, think about what is the density matrix of what you should see after we open the box. Okay. Well, actually, that's true because we'll know which one it is. All right. But what we expect is a mixture of the two. Right? So classically, we do this lots of times. Our description of what we get after the box is half the time it's going to be active. And half Sorry?
What are we going to do with all of these cats?
You could use the same cat.
That's one of the questions that you have to answer in the ethics form. What are we going to do with all the cats?
Where are you going to find these cats?
This is the density matrix expected.
I don't know,
You can't even
afterwards.
write the state down you expect to get because it's going to be one or the other. You know, right? You can't write mixes down in
Physics
stacks.
biology, enjoy it.
No, back. So how could you determine whether it was a plus or a minus? How could you do that? Figure that was the case after all.
Put the cat through a beam splitter.
Right. So you need a device inside that box before you measure it, right? That can do an interference experiment with every part of the cat. Right? That's obviously hard. It's much easier if it's a photon or a half system. But ultimately, it's just a technological challenge, right? Just a technological challenge. Do the interference experiment with the cat. Can people swallow that pill?
Well, if you can get the cat into a vacuum, sure.
Yeah, it's got to be completely isolated because what happens if you entangle with anything that you don't then have part of your interference experiment?
Can't you make the measurement before you let the photon get and kill the cat, and then put it in the state so that it'll evolve into that state rather than measuring it to be in that state?
Well, that'll give you both.
Hang on. If you measure, what do you measure?
Well, because presumably if the photon was in a particular state to begin with, you could
Yes.
force the cat to be in the A plus D or A take day. So just do the measurement on the photon and let it evolve into the state rather than let the photon be possibly in that state.
I'm actually confused. How do you make the cat go into A plus D?
Because if the photon's in a particular state to begin with, when it
Yes.
goes through the beam slitter, instead of measuring whether it goes into one or the other, which would give you either alive or dead,
Yeah.
you could measure something conjugate to that, so that you know the photon has the
Okay,
phase.
so part of the problem there is that our particular setup, we're hitting it into photodetectors, which are actually, they absorb the photons. The photon's
Okay.
gone. But there are kinds of measurements you could make where you could indeed, like, entangle the thing with the cat and then measure something odd, and then you would measure the cat. That's absolutely true. Okay, so, and that's effectively how you do an interference experiment. But all the technical difficulties are still there. You have to keep that, you have to have that entanglement be perfect, and you have to keep that whole system completely isolated. Because if you further entangle with anything else and trace over that extra thing, what you have is a mixture again. Okay, yeah?
Cats all have mass. Do you have to keep gravitational outside as well?
Yes, well you have to, it has to be completely isolated from anything that can entangle with it. Okay? To the extent that it will entangle. Obviously, the tiniest, weakest thing over a finite amount of time won't have a chance to entangle. But yes, anything that is strong enough to entangle is got to be isolated.
So you drop the cat so it's in freefall. Yes.
Yep, the cat has to be in free fall. Yep.
Dumb
That's in
question.
space.
How do you work out what the phase is from the interference vectors between the like plus and minus?
The normal way, right? So if we use Damon's indicator and we entangle a two-level atom in a particular way, so up means active and down means dormant, then we just measure sigma x. And if we get left, then it's probably right on most people's usage of signs. We'll know it's in A plus D, and if it's left, we'll get A minus D. Yep.
But it should actually be pretty easy because you can just, as long as they're causally not related. Like if you got your friend to set up the experiment so that you're like, I don't know, far away from the source of the photon and the Schrödinger cat's on the other side of the universe, far away. The photon comes from the source. You can measure the photon, and the photon also hits the cat, like half killing the cat or whatever,
It's
then
been-
you're still not causally linked to the cat. So you're not interfering with. You can't.
It's still a matter of isolation. Like you need to interact with the cat, and the cat mustn't interact with anything else. That's the hard part. You know, cats are big and they sit on things, and the thing that they sit on, they're entangled with, right? They
As
can
long as
tell.
the speed of light and you're too far away that nothing can have reached.
Right, yeah, but you're talking difficult things now, right? Those are difficult. Putting cats.
I've lost a
All
cat
right.
space.
But in principle, but you're absolutely right. There's nothing theoretically challenging about it at all. Right? The cat has two states, right, and some extra structure we're ignoring, right? It's just a two-state
He's very simple.
entangled like we do all the time.
Experimentalists can't do easy things.
But it's technically quite difficult.
Just trace over the cat.
Okay. However, we've got a photon detector in our device. Right? We believe a photon is in a superposition. Why do we believe that? Because we put mirrors there, we can get interference fringes. All right. Do we really believe those detectors? Surely those detectors are measuring the photon. If they measure and the wave function collapses, what do we have?
Measurement.
Yep, one or the other, right? We have alive or dead from the start. Okay, but we know from von Neumann's chain that that can only happen if the detectors have some magic, if they're not described by the Schrodinger equation. Okay, so we know that if we follow the Schrodinger equation, that doesn't happen. But our rule of thumb says that does happen. So we need to know whether that happens. And of course, a cat's bigger again. And cat has this magical, you know, if we have magic that collapses wave functions, then presumably cats have it. Maybe? Is the cat a measurement device? If the cat's a measurement device, then it's not alive plus dead. It's alive or dead, or it's active or dormant. Okay, whatever my A and my D mean. Okay? So, we need to know, right, whether this is magic. And it's not awesome having magic in your theory, right? Now, electric fields are kind of magic, right? So there's plenty of things that we invented as magic. The Higgs field is certainly magic, right? So maybe we shouldn't be prejudiced against magic. What we should be prejudiced against is things that we haven't worked out properly. Okay, so how does it work? Like, if consciousness works, how does it get attracted to lumps of protein and very fancy computers, right? Like, do I really take a bunch of things without consciousness and string them together and suddenly have consciousness? If it's a real thing, if it actually affects stuff, then we can detect it. Right? We're just saying it's a physical thing. Okay, who believes I can move this pen with my mind? Hands high?
You just
Power of my mind?
You just did.
Well,
Yeah, that's right. Here I go. Right, I did that. Was that amazing?
Yes.
Okay.
No.
Even I said that was
From first
amazing,
principles.
right? Kind of believe in consciousness. Because, or possibly something outside. Because if I think of myself as disconnected from physical reality, then the fact that I can send nerve signals is pretty amazing. It means I have the power of electrodirection. Okay, I can move electrons. And sure, I use a special amplification system to move this pen. Right? I had this one built, right? It takes little electrical signals in here, makes them bigger, fires, specially prepared charges of energy reservoirs and so forth. Right? It's a device I built to amplify my ability to control electrical signals. But I have the magical power to control electrical signals. And surely, you know, if I can get a, whatever it is, microvolt, surely it's just a matter of time before we build a consciousness that can do megavolts. Okay. Yeah? Or, that's one way of looking at it. Or, another way of looking at it is, I'm just a bunch of chemicals, right, in this arrangement. Okay, so this is an interaction of a bunch of chemicals, and really it's my sense of self that's the sort of interesting thing. Okay? In other words, do I obey the laws of physics or don't I? Okay? In my household, everybody obeys the laws of physics. All right.
How dare you?
Your son is mine.
So let's have a poll. Who believes that we obey the laws of physics? Who believes there's something, and who believes, and you may find that you put your hand up 2 times if you haven't thought about it, who believes that there's something more to them than the stuff that's arranged on your chair? Yep. Talk to me about that, Ruby.
I find, so like you have some people say, we're a bunch of chemicals, how
Yep.
can chemicals choose to react? But I can imagine a world where a bunch of people walking around acting like people
Yep.
with nothing in there.
Yes.
But just if you looked at it, you couldn't distinguish it, fine.
Yep.
But we've got consciousness.
Yeah, yeah.
And that seems very weird.
Doesn't it?
Yeah.
I agree.
Are you sure everyone else is conscious, Ruthie? Maybe no one else is conscious. You're the only conscious.
Yeah. We're a figment of your imagination.
Yeah.
So the real question is consciousness a thing that interacts with the world, or a bunch of experiences at some level? Like, is it an arrangement of stuff that happens in the world? Like, is it a pattern? You know, is it sufficiently complicated computer program consciousness or not? Right? People have, I think, the general. Ben, do you have something to? Yeah. Same way. Okay. Yeah, I totally agree. Consciousness is a very weird phenomenon. Okay. On the other hand, a lot of people are kind of uncomfortable with the idea of, you know, that's the thing that collapses quantum states. Okay. Should we jump? So just to, we've done that one. Yep. The basic idea is you have a beam splitter, you put a photon through it, it goes into superposition, it hits some detectors, which go into superposition, that hits some computers and cats, which go into superposition, and then the conscious thing, right? It takes a physicist to really collapse away from it, and suddenly you have quantum branches.
Is that why no one else discovered quantum mechanics?
Maybe. Okay, that's one idea, and maybe the cat's conscious, so maybe the chain is there. All right. Or maybe physicists aren't even conscious. Maybe there's just one thing collapsing away, so you have to go further down the chain. Maybe there's just like one uber consciousness that collapses. Bring it on down. Ding ding. That goes into superposition. We go into superposition of thinking that the cat is dormant and the cat is active. And then finally we get real consciousness and bang. Okay, so lots of attempts have been made to make theories that don't have magic in them. But they don't have, and by magic I don't mean weird fields, because of course our theories are full of weird fields. What I mean is stuff we're not bothering to explain. In other words, let's not have a rule of thumb measurement postulate. There's this thing out there, it collapses wave functions, don't think about it too much. It's all right, why do wave functions collapse? And so the idea is that wave functions are always collapsing. All of them, all the time. So the way it works is you have some fundamental particle floating through space. It's got some wave function. It obeys the Schrodinger equation, but it also has a stochastic process that collapses it. Not infinitely, but a lot. Can you sort of picture that?
That doesn't make any sense.
It's a Poisson jump process.
But that makes no sense because you've got both x and like position and momentum. So if it's constantly collapsing in position, you've screwed up the momentum and vice versa.
Correct. It will screw up the momentum. That's right. That's what it will do. Yep. And so it has to do it in one thing. So it has to be actually a preferred basis.
Also, you can't normalize.
No, you normalize. This is just different, but I can't normalize. That's true. I'm just showing you the shape. All right. So you're right. There's a preferred basis. Hands up if you like the idea of there being a preferred basis. Hands up if you think it means the theory is automatically wrong. All right, two of you got your hands up. All right. There can be theories that make. We're just getting the ether back, right? Space is special. We all know space is special. All right. So how it works is, if you have one of these particles and that process, well, why wouldn't we have seen that already? Why wouldn't we have lost all our quantum effects?
It would also break time reversal.
Yes.
So you can say there's good reasons it would automatically debunk.
Well, time reversal, time symmetry is not preserved anyway, right?
Yeah, but there's close enough ones that you'd be breaking a lot. You'd be losing information constantly, and
Yes.
everything would break.
No, everything would lose information constantly. All right, this is
But
relative.
it'd be a very strange. It would be experimentally ruled out very quickly, except for tiny.
One of the
tiny.
big mysteries of the universe is why does time seem to flow in a particular direction, right? This one makes it easier. Okay, so obviously, entropy is going up because that's the way the jump process goes. Okay. Now I totally agree that these are issues that make us uncomfortable, and there are more to come. Right? The ramifications of this make us very uncomfortable, but let's be open-minded, right? We're trying to deal with magic jumpy wave functions. Okay, so we're trying to come up with something mechanical as a solution. Okay, so why haven't we seen this already? This would mean that if we entangled some things, right? So if we have a real entanglement with a real thing, it's got like 10 to the 23 particles, so it just collapses. And so we would get wave function collapse, more or less. Okay, so why wouldn't we have seen this already?
You guys have this one.
I'm not.
I mean, doesn't that kind of explain the classical world? Like these
Yes,
things
yes it
don't-
does. That's the whole point of it. Yeah, it explains. That's what the classical world means. There's lots of particles. You've got lots of particles. Looks really single valued to me. Yay! That's what I experience. I experience single world. Therefore, this theory gives me that really naturally.
Everything's entangled with everything else, though. So, like, it'd be very hard to make a.
Well, this would stop that happening too much.
But no, it's still everything. If you interact with something, you're entangled with it.
Yep, and then it would
So
poof, and
you'd
you'd
have
be in
to-
one or the other.
it'd
So
be
every
very-
time you interact with something, you get one or the other. Why wouldn't we see that for small things?
There's less entanglement going on.
Well, they could be just as entangled. They could be perfectly entangled. You get two level things, we can perfectly entangle them.
You're less likely to collapse if you've got less things in it.
That's right. So you do it spontaneously, not too fast. If you do it too fast, we would have seen it for the quantum things we've already looked at and saying, hey, they can be in a superposition. And obviously not too slow, or else it wouldn't explain why all this stuff was classical. Yeah? That seems all pretty good. All right. So this is the weakest song, but it does have a edge in it. See the famous callback? All right. Okay. All right. What if quantum states really collapse all the time? Random processes, well, as Schrodinger's equation. Basic particle has a chance to collapse in each moment. Big entanglement surely is gone in a flash. No need to define measurements. We entangle and we know where it lands. Everything is quantum and simple. Oh yeah. Random process is slow, making small things one. Measurements involve so many bits, they're classic. In between we will see there is loss of coherence, and our theory is fully defined. But theory won't conserve energy. It contradicts relativity. What is simultaneity? Yeah. So you'll also note that these wave functions collapsing at a particular time is a hell of a non-local process. For something spread out over space, what does at a particular time even mean? Right. By which I mean it doesn't mean anything. So that's kind of balked. So you have to come up with a relativistic safe version of them. And one final coffin in the emotional nail for me is it doesn't actually completely destroy the entanglement. All it does is get rid of most of it. So you have those two branches, and he's like, well, that one's really small now. Small? Fine. Why? That's not actually classical, that's just quite classical. Agreed? Okay, so what are we going to do? How's my time? 11. Okay. What are we going to do?
Wait, Joe, sorry.
Yeah.
Oh, why doesn't it conserve energy?
It doesn't conserve energy because when you compress in position, you expand your momentum. You write this process down, it heats. It's momentum diffusion.
Do we have that problem with regular quantum mechanics?
No.
The wave, we do, but the wave function collapse happens when you measure, so presumably that's where the energy comes from. David?
There's no problem because the same thing happens in classical probability theory. You get wave function collapse in a classical probabilistic theory.
Yep.
Your quantum probabilistic theory should act no differently. Therefore, you're actually stupid to expect it to act differently. you need to look at what the reason is it collapses for a classical probability theory, which presumably is because you assume if you make a measurement twice, you get the same answer. And so it's that assumption that if you make a measurement twice, you get the same answer that gives you wave function collapse.
What do you mean you get the same results as a classical probability?
Okay, to get a classical probability, you use the Liouville equation and it evolves linearly under a Schrödinger-like equation. You can actually write it exactly in the same framework as the Schrödinger equation.
Don't you get like Bell's inequality and stuff that you can't get classically?
But that's irrelevant. That's a red herring here. Like, it doesn't matter Bell's inequality. That doesn't actually matter in this situation. All Bell's inequality means is that you can't represent it as a classical probability.
You can get correlations in quantum mechanics that you can't get classical.
Oh yeah, but that's not actually relevant because quantum mechanics is a strict generalization of classical mechanics. Sorry, quantum probability theory. Let's remove the mechanics because mechanics is actually a red herring here as well. Your classical probability distributions are your quantum probability distributions are a strict generalization of your classical probability distributions.
So can I just add a little detail there? So you can write quantum theory as almost a probability theory, a normal probability theory. So instead of having a particle having a wave function, it's just got some kind of probability distribution. The reason it's quantum mechanics and not thermodynamics is that there are rules to quantum probability theory that you don't have. In particular, you have non-commuting observables. And in the presence of non-commuting observables, you get some kind of weird abilities to make correlations. Okay? So this is what contextuality is all about. If you want to, that's the key word if you want to look at this. And what Damon is saying is that essentially, actually, underneath what Damon is saying is that our model of the world is allowed to act as weird as we like. Okay? So a probability theory, if I take a box, right, and another box, and I've got a pair of gloves, and I put one in one box and one in the other box, right? And you don't know which one is left and which one is right. And I give one to Kieran, and Kieran goes off to Alpha Centauri, and he opens his box and he sees a left-hand glove. What happens to his probability distribution of what's in my box? It collapses, right? And that's kind of what you're getting at, right? Probability collapse happens upon measurement. Okay, so why are we fussing? We're fussing because we need to know when that is. We need to know when that is in order to make our predictions correctly. Okay, so measurement itself, if we're allowed to not define measurement, all of these things are unnecessary. When we realize we have to define measurement, then we're done. We're in trouble. Okay, so we tried to define measurement. All this really classical stuff, I know what it is. Well, actually, there isn't classical stuff. There aren't really particles. There are no hidden variables. You can't classically collude your answers. You still have to have something apparently non-local going on there. Right? That's what our game today started with. Right? And it was, well, maybe there's just something that collapses wave functions. All right, well, you still got to define that. Okay, maybe it is consciousness, or we'll call it, the binder field. Right? But we still have to define what it is. Right? We might as well just define measurement. Okay, so this theory, the advantage of this, is that it actually explains under what circumstances wave functions collapse. And exactly, so there's no such thing as having to explain what a measurement is if you're taking this theory, because if you entangle a big thing, it collapses. It mostly collapses. Right? So it's just entanglement. So the apparent similarity between entanglement and measurement is resolved by saying, well, they're the same. Okay? And they behave the same in that the quantumness goes away if you entangle enough. That make sense? And its problems, the fact that it basically doesn't behave relativistically, and therefore it's terribly defined. People have tried to make relativistic versions of this. Okay, it also doesn't conserve energy. There should eventually be the ability to detect this. There should be some size of entanglement we make that there's a kind of deep noise floor built into the universe and the dynamics itself that stops us from ever making a bigger entanglement than that. Okay, so there's a deep decoherence process. Yes?
Can it be possible that it's local on a higher dimension than the Earth? Like all your particles or your wave function exists on a higher dimension and it just appears non-local to us in the Earth?
Well, it's entirely possible. They have Hilbert spaces have a lot of structure beyond the spatial dimensions.
Yeah.
And you're asking what if there are other continuous degrees of freedom as well?
That's right.
Okay, maybe they could be, but they're still behaving non-locally in our spatial ones, right? Being local in those doesn't help if you're still non-local in ours.
Or if there's like another spatial dimension that we can't see or something.
That would still break locality. That would still break locality.
That's string theory, but it doesn't, like, if you can just picture that in a reduced dimensional sense, if you're saying this thing appears to affect that thing, if you add extra dimensions, that thing is still affecting that thing. The only thing you can do, the only way you can stop that being weird is if you can make somehow all points the same. So you actually have to collapse the spatial dimension in order to get rid of that weirdness, not add more dimensions.
But you could see that.
Yeah, I know what he's saying, but it's stupid.
Yeah.
Be able to access all of those points.
Because
Are you saying
when you care
everything
about
is connected to
you only
everything
care about
else?
three
Kind of,
dimensions.
you could-
You don't
Well,
care
like,
about
yeah, you can't interact with
if you
it.
were
Forget.
It's
All right,
not-
so what you're kind of doing there is you're equating all
physics.
points.
Yeah.
Equating all points in
Right, okay.
And then
Means you can get a more accurate mathematical model than it is.
Well, no, because it's either like
Then
you're breaking
there's no
locality,
such
like
thing
you
as
are breaking
causally
locality in a
unrelated
different sense.
elements.
So unless you can say that
Which
locality doesn't
is
exist,
not really our experience
which is
thus
always
far,
possible.
but I guess
Yeah, that's basically what it's
something
saying.
like that.
Yeah, but then you just ignore locality and don't try to make a stupid model. Just assume
Exactly.
assume it's broken.
You don't need
we're pushing the
you don't need
fringes
another
all the way
dimension to do that. That's
Yeah,
easy.
you can just
Yeah.
We should be looking for something.
just shove in a second term into
We
Lagrangian.
could be looking for some ether theory. All right, there is another way to go. All right, yeah.
Just if like you can just make non-local theories really easily. You don't need to shove in any extra dimensions.
Yes.
Yeah.
He's
so-
trying to make local theories.
You like. I think the only way of meaningful local is to look at 3 dimensions because we don't care about what happens in hidden dimensions.
Yeah, what he was trying to say was that all points along our 3 dimensions are in fact co-located
In some,
because they're connected by an arbitrarily small distance
yeah.
in some other axis. Which you have to explain why quantum can do that and nothing else can. And if there really is a causal structure along those spatial dimensions, that means we've got time travel and all sorts of cool stuff. Which means we've got to explain why those paradoxes don't happen. Right? If you can go backwards in time, you have all sorts of issues to deal with. Okay. All right. So there is one way to go. And to understand that, we actually have to tackle an emotional issue. And that emotional issue I've already been kind of teasing out on the side. Supposing we're going to do the Schrodinger U experiment. So the Schrodinger U experiment has U in the box. Okay? It has U in the box, and one side activates a sleeping gas.
No, you can do anything.
Of this thing. And so, from people outside the box, right, they're going to assume that there's no wave function collapse going on until they measure it. Right? They haven't measured it yet. Right? So they're going to treat U quantum mechanically. Yeah? What do you experience?
Well, I've never experienced
You would stay alive the entire time. You wouldn't die.
Classical trajectory.
Well, you would.
Yeah.
Well, you die if you
you-
died and you'd stay alive.
You would stay alive the whole time because if you
Yeah, no,
died,
you'd stay alive
you
the entire
don't-
time.
Okay.
But if you die, you don't experience it.
All right. Supposing it wasn't a presence or absence of thinking. Supposing it was active or sleepy. All right. What do you experience?
Always sleep. Presumably. Always sleep.
Presumably you experience one or the other. Doesn't matter. Who agrees with that? Hands
Yeah.
high.
You just experience nothing. That's fine.
Justify, James.
Well, it just seems logical.
Seems logical. I've never experienced any other things other than a single experience. All right.
Can we go and do this? Does someone want to volunteer?
Yeah, I'll volunteer.
We swear we'll use sleeping gas.
Okay. All right. So now we have to unpick this idea of identity. I'm afraid I don't have a song for this one, so we're going to have to do it otherwise. Oh, I'm sorry. And everyone's like, relief, 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 fake pity, relief. Okay.
Good. I hope this video goes off on
All right.
the reference moment.
Nathan, what makes you? What makes your experiences?
I don't know.
All right. Riff on the idea. The question. What doesn't?
Akil's experiences are not my experience.
Okay. All right. Why is that?
So I'm not Akil.
Because you're not a keel. All right. So we have a fundamental distinction here. All right. But we know you're about the same size, about the same mass. All right. We know that the particles making up your various bodies are at a very deep level identical. Okay? The wave function of the universe is not changed if I swap any two of them. All right? The particles that make up your body now are mostly, for the most part, not the particles that were making up your body 10 years ago.
Yeah.
All right? What are you? What is it about you that makes you not a keel?
Don't know.
You don't know.
I'm sure.
If I were to take all the particles in your body and arrange them in a line alphabetically, would that be you?
I think that wouldn't be.
That would not be you, all right? What if I were to then rearrange them into the exact configuration that a keel's molecules are in? Would that be you or a keel?
I have a slave.
Would you be a slave? This is the key question.
Probably be a kid.
You'd probably be a keel. All right, so actually there is a kind of answer coming out of,
So
right?
arrangement stuff.
Who thinks that might be their answer? That you are a particular arrangement of these atoms.
But then
I don't like that.
It suggests that you could clone yourself, and then are you somehow experiencing two experiences because you've got two identical.
Yeah, but
And it is
as soon as you
precisely
clone,
that
they
point
different
change.
person,
we need to
yeah.
address before we can reach the truth. Yes, same.
But yeah, but as soon as you cloned it, the second one would have different experiences. You'd be functionally different. It's just like a computer program. You can clone them easily.
So let's imagine we are indeed going to be faxed. Okay, so the new Telstra teleporter looks like this. You go into this box, and they very carefully read the full state of your body, and then they think, all right, we have a big tub of chemicals in Brisbane. They arrange into the exact copy of Joe. Right? Then they do some checks, and then the red light goes on here, and it says, "Please step through the red door." Okay, we need the chemicals. Okay, if I do step through the red door, these atoms are rendered down into chemicals. To the world, it looks like I stepped into this one, and then I stepped out of a booth in Brisbane after a fibre optic link.
You're trusting Telstra with your
I'm
life.
trusting Telstra with my life. I should have prepared the song, but there's actually a song by Douglas Adams, roughly about this. Altez, Aldebaran is great, you know, and Altez is pretty neat. And Beetlejuice's pretty girls will sweep you off your feet. They'll do anything you like, real fast and then real slow. But if you have to take me apart to get there, then I don't want to go. Right? Which, the idea is, you get into this box, and the light goes on and says, "Now step to the red door." How do you feel about that, James?
Well,
You're like,
I would be,
there can only be one of me, therefore it's fine that I step through the door? Or do you think, no, there's two of me now, I want to get out, How do you feel? Yeah, the second one, right. Or your soul hasn't been copied. Right? Or Telstra missed something. Right? There's a special consciousness field. But if the consciousness field is real, then it has some physical effects, which means they can measure that too. Right? And they copy that too, and they make that. Yep. In which case, they've made a copy of you. There's two.
Who are going to duel each other with bloody pipe pistons.
Okay.
Fight to the death.
Yeah, they can duel. Yes.
Yeah. And then it's like, no, we're just full of it. It's like, I was worried.
Well, it starts from there.
Yeah, but if
That's right. It starts from there.
They talk about other
So you're walking in. Leave it on if you can. Ethan. I think we're going to.
Yeah, I just want to check to make sure we're not.
Are you able
More
to
bullshit needed to.
like, make the copy and then retain the same structure in the original?
Okay, so let's now talk very briefly about quantum teleportation. So I've done work on quantum teleportation, and everyone in the public totally misunderstands what it is. So supposing you can make the facts, that's probably going to do, unless there is actually entanglement going on in our self, right? Unless we are funky, delicate, fragile quantum flowers, right? A good classical measurement of us would probably do. Right? If I take some electrons and move them around in you a little bit, that probably won't kill you. Right? And if I take one out and trace over it, I probably haven't ruined the beautiful experience that is consciousness. Right? We're probably robust, which means we're probably classical. But suppose we're not. Then what we actually need to do is we need to get the full quantum state of this and get it to Queensland. Can that be done?
Yeah.
Not without teleportation.
That's quantum teleportation.
No cloning theorem.
There's a no cloning theorem, which means we can't have me in the box in both cases. So to do proper quantum teleportation, you actually have to destroy this in the measurement process. You can then send everything classically, the information classically, provided you have entangled particles to begin with, but they can be boring old, yep, I definitely have entangled particles. The classical information can be sent, and then the thing that walks out here can be a full quantum state copy of Joe. And the chemicals have been reduced in that process. So that's doable. Okay. But what we're really, there's another
But
complication.
surely if you're that concerned about perfection, then every time like a gamma ray hits you or you walk around or stuff, you die. Because
Well,
your quantum state is changed so sufficiently.
People
it's
are
impossible to
people are
consider.
very clearly irrational about many things. So let's. And if
Well,
I'm
I'd say it's probably likely we'll
if
die.
I'm giving my soul to Telstra, I do want to be pretty careful.
At the point that we can
Okay,
teleport
so what we're
functional
actually going
understanding
for
quantum
here
things, everyone would.
is a sense of if our experiences really are this state, if they really are this state, then if I make 2 copies of me, then there really are 2 people, right, going on. Do we believe that? Who does believe that? Or thinks that's reasonable at least?
There's 2 people.
There's 2 people. If I make a copy of this stuff, there's 2 people. Hands high if that's where you go. Alright, so Dell's the only
Introduces us to
dissenter.
our clones.
Talk to us. Okay. Alright, so
I just saying, make a copy of this.
Yep.
There is now 2 people.
there's now 2 people. You might not necessarily call both of them James, but you have no reason to choose one of them to be called James or the other, right? And there will now be 2 different Jameses. For example, one might get some sleepy gas. Okay? Okay. All right. So supposing we're the state, and we're in this box, we haven't got another bunch of atoms in to make another one of us. What have we done? We've taken the same atoms and we've put them into 2 states. Same number of atoms, 2 states, with a coherent relationship between them, by the way. But that's not important right now. How many people are in that box? Or, alternatively, how many different experiences are in that box?
2 experiences. 1.
2. 2 experiences. What's a person? If not an arrangement, right? So they've got half the norm they used to have, right? But there's still 2 of them, right? And then when we open the box, we collapse the wave function, and all the norm gets sucked up into one or the other. What do you reckon about that?
Why is the guy outside the box?
Well,
Yeah,
Why is
if
he
it's,
more?
by the way you describe that, it sounds like the 2 people with half the norm could still interact with each other.
Well, they can't. All they can do, you can do an interference experiment with them, but of course, if they're obeying the Schrödinger equation,
Keep getting there.
then it's linear, so they
Tell
can't.
from this week's
Right.
lectures.
Yeah. So as soon as they've been put in a superposition, they're in a superposition. There's just 2 now. At the end.
Do you believe
right?
in like
Unless, yeah.
Well, that's kind of
That's not
beautiful.
what I think.
Not an
But
Everett, though.
is it true to say that all of
No,
these
Bayesian,
paradoxes,
I think that's
everything
probably
goes away
Everett, I don't know.
if
It's
everything is
close.
from the very start? If everything is
I don't see this fundamental difference
We're
between
going
quantum and
there. We're
classical
nearly
probability
there.
theory.
We're trying to get rid of all these
Communicating
paradoxes just by giving up our
When
last
you
shred
observe
of
it, I
sanity.
postulate that
Yeah,
they see the
there's
same
a
thing on
game
one,
called
two
Hitchhiker's Guide to the
measurements
Galaxy
at the same
game,
time.
like Infocom game.
And that explains
there's
everything.
a thing you can't do unless you get rid of the particle of common sense from your brain. And we're just trying to do that now. Yeah, take it.
If you had a
You know what I
photon
mean? Everything's explained. You just
traveling
assume
out in a
that-
superposition, you wouldn't say that there's 2 photons. would you? You'd just say there's 1 photon, but it's in a...
I would say there's 2 states.
Yeah, there's 2 states.
Right. So I'm not saying there's more atoms.
Yeah.
I'm saying there's more people. Because I've decided to call a person
classical probability theory.
an arrangement of
You have a
atoms.
probability
The 2
distribution.
arrangements, I'm calling that 2 people.
Yep.
Okay?
You don't
Effectively.
claim that the probability distribution is the same.
So what do you reckon?
What you assume is that it jumps to all possible states.
We actually go
X is
back
that
to the
X.
chain.
Yeah, so that is
It doesn't make sense that when you open the box, it
That's that-
collapses.
Does it? That doesn't make sense. So let's go back to the chain. Right?
Doesn't really work.
Well,
Like,
yeah.
that's why I take the probabilistically
Okay,
realistic
back to
interpretation. Just
So
because you
here's-
found your particle at X doesn't mean
here's
you
the
can backwards
photon.
interpolate that it was at X before
Right?
mentioned.
Here's
It's
the
not meaningful
person
to
in the
say.
box.
And that
They get
gels
entangled
with
with the
baby.
photon. There's now
Exactly.
2 people in the box. One of them is in a state where they're thinking, huh, kind of happy that sleeping gas didn't get crushed. And the other one's thinking,
It's the people reach into it.
and then the person outside, they open the box and they start interacting.
No, more so it is fundamental.
What do they see?
Once they found it in X, the deal is in X. Looking backwards and
How many of
calculating.
those people are there?
That's what I mean.
Yeah, and I'd say
So what you have
just
is
remove that
photon
ability, and quantum mechanics
and
is not
that
unreasonable.
sleepy gas, sleepy person, entangled with person that saw a sleepy person. This all looks beautifully consistent, doesn't it? That looks like a lovely dusk world, doesn't it? Right. Plus I times no sleepy gas, awake person, person that saw an awake person. That looks like that, right? How many experiences are there? Two. Okay. Alright, lays forward is probably just
I think the most sensible interpretation. Like if the good is what says, are the other ones real?
Yeah.
I'd much prefer to be like a non-real Everettian, but a real Everettian. But
So what we can do is we can actually explain what we see without any wave function collapse at all. We just take that postulate away. We just have everything's the Hilbert space, linear evolution. Any questions? All right. So everything that explains everything. There's no non-local. There's no relativity problems anywhere. Okay? What's a measurement? It's just when you entangle some things. Why does it look like it's single value? It's like, because you get entangled. If you're entangled too, back to that chain, remember that chain, you see something consistent, right? That's why it looks like that. And it turns out that if you're going to try and predict what happens next, the only, and you kind of weight it by how much amplitude you have in your wave function, the only rule that makes any sense, in other words, the only rule that obeys the laws of probability, is the normal Born rule, our rule of thumb. So that third postulate is not a postulate, it's a rule of thumb for saying what you expect next.
Well, it's sort of a given situation.
So, here's the box. I walk into it, I'm measured, I'm copied. There's going to be 100 copies of me, and we're going to be put out in a big field. Okay? One of us... yeah, and one of us is going to be shot in the leg. Okay? Alright. I get in there, I appear in the field, and I'm shot in the leg. Should I be surprised?
Yes.
Hands up for yes? Hands up for no? Okay, explain no.
Well, you should have expected a certain...
Yeah.
When I'm walking into this box, when I'm walking in, I know 100% of the time someone with my exact experience is about to be shot in the leg. Bam! Well, I knew that was going to happen. Alternate point of view. You're standing in a field, there's 99 of you who haven't been shot, and one of you that's just been shot, you're like, yeah. Yeah. It was most likely not going to be me. What if it was 1 in a trillion and you were shot in the leg? Would you be surprised?
Very.
Bit frustrated.
Like it's a 1 in a trillion chance you would be surprised because it's very unlikely.
Okay, so it's really important that you condition your statements on who you are. When I'm walking into this box, I know for sure someone's going to be shot in the leg. Like I am, in some sense. Yeah? Alright? But I'm predicting, when I think about what's happening next, I'm going to be one of those people. And so you condition, you have to kind of weight your probabilities, your expectations on your chances of being each of those people. Right? Now when it's discrete, it's like a million people's a million chances, a million microstates. When it's continuous, it turns out it has to be the Born rule. Okay? It has to be mod squared of the amplitude. Okay? That's the Everett interpretation. I set myself up in my Schrödinger me experiment, thing goes in, I expect 50-50 to get sleepy, because that's the mod squared of my wave function. So what's going to do? So you behave the same way as if the rule of thumb is real, but any external observer could do an interference Joe experiment and show that I'm actually awake plus dormant, or awake minus dormant. Yeah? That's the Everett interpretation. Its advantages are it's fully defined. We don't need to define a weird measurement thing. Okay? Its other advantage is it does conserve energy, it is completely local, it doesn't fight relativity at all, it has less postulates. So it's cleaner. It is in fact the only fully defined theory we have of quantum mechanics. is it many worlds?
Copenhagen's not
It does a bit, doesn't it?
No, because you're defining with measurement collapse.
Okay, second slide. Actually.
It's not.
Back. Okay. So this is a quote by Douglas Adams, who was freaking awesome and basically knew what was going on. He said the first thing you realize about parallel universes is that they're not parallel. Okay. It's also important to realize that they're not, strictly speaking, universes either. There's not lots of worlds in the many worlds theory. There's one world with the same number of atoms there ever was. They're just in a big complicated state. Okay. So it's easiest if you try and realize that a little later after you realize that everything you realize up to that point is not true. Okay. Which we've got to, I think. Alright? So the many worlds theory is very badly named. There's many worlds in that kind of, if you think of a world as a classical bunch of stuff that's happening, yeah, I guess you're in a superposition of those. Alright? We couldn't show, because the evolution is linear, we could not show that we're in a superposition with other branches. They're just there. Okay? All we can do is show, perhaps, that we could be put into a superposition in the future. There is a way of doing that. Okay? Questions? Okay.
Yeah, there's more to find. Yeah, exactly.
All that I am and all I'll ever be is a state of a body. All that I know and all I'll ever see will stay tangled with me. All I've heard and it's true. But there's no collapse, there's just me and you. From here we will go in all ways. But I'm happy to be floating in Hilbert space. And I won't mind if you're holding my hand and you're both linear and we don't give a damn. QM seems fine with no axiom of mystery, just one rule of thumb to predict what we're gonna see. All that I am and all I'll ever be is a state I call body. I live plus I die plus I run away. It's a beautiful story.
That is all I had. Well, my shame is reducing. I can now tell you about the quantum suicide thing, which is kind of obvious. I can't do it on record, obviously, because if then one of you nipped off and killed yourself, I'd be probably in a lot of trouble. So there's lots of emotional problems with this. People have a lot of problems with the idea that everything is now happening, that all possible futures exist. You really have to take into account the fact that you have to act on any reasonable sense, like there's 1 in a trillion of you and only one of you is going to be shot. You really have to follow the Bourne rule. If you were not to do that, you could do something like buy a ticket to the lottery, build a machine that kills you if you fail. Now in the classical world, what happens is you probably get killed and you probably fail. What happens in the quantum world is you definitely fail, plus you definitely live. So you definitely wake up the next day rich. Hey! Plus, all your friends definitely wake up the next day seeing you built a horrible machine that killed yourself and feel terrible. And so that's all true as well. Okay, so don't do it. Ways we might find out eventually this is true. Supposing you step out of the road and you're mysteriously missed by a bus or your quantum tunnel through it, just when you did something stupid. Right? You think, well, that wasn't very likely. And then you have a heart attack, and then you invent something just in time. And you think, well, that wasn't very likely. Or your heart rearranges itself. You go, oh, that was kind of unlikely.
No one will believe them.
Well, in fact, all those things are definitely going to happen. Right? If the Everett interpretation is right, they're going to happen. Right? Plus, you're going to die. Right? But the existence of this tiny little low norm thread that keeps on going is a feature that you really only get in the quantum theory. So if you turn out to be immortal, start believing you're immortal. Yeah.
So those people who won the lottery like 10 times have mastered quantum mechanics.
Well,
no, they
not the way we know it.
Thing is,
mastered something.
You'll be immortal, but no one else
You have to
will.
look at the numbers involved here. It is much
Cheating.
more likely,
It's
of course,
incredibly
that you'll
depressing.
tunnel mostly through the bus and you'll be in agonizing pain forever. In
Most
order to
people
work,
will
all
have
you need
mother
is
done.
consciousness. And there have been some nasty sci-fi stories written about that.
So,
Pardon?
Joe, we're constantly in one branch of this tree.
Yep. Yep.
Measuring things, certain probabilities,
Entangling ourselves with
inventing
things.
laws of physics, or seeing how the laws of physics work.
Yep.
But other people in other trees have different things happen a little bit differently. They would see laws of physics a little bit differently.
Absolutely.
Are you claiming that there are laws of physics that work probabilistically across all the systems, or because I mean we would develop completely different laws? So what is
Doesn't
like
make sense.
this whole theory?
So if I have a coin and I flip it and it turns up heads 13 times in a row, what do I think this coin does? I can probably assume it's biased, or it's all.
You have to follow quantum mechanics.
But at the same time, people have done experiments of how long it would take. So if you just flip a coin, how long do you get 10 heads in a row? And if you do nothing but flip a coin, it doesn't take like a couple hours.
Right. So you're absolutely
Yeah,
right.
so
There will be people in the universe who can't discover science and how it really works because
But they exist already.
keep having weird shit happen to them. But they are an increasingly small fraction of the norm.
So how do we know that we're not the special ones?
That was-
It's just very likely.
It's always a problem though.
We don't.
Exactly.
Yeah.
It's just a predictive, but science is only ever a predictive tool. So supposing we've got the box and we get in there, we get out, there's 100 of us and we're shot, and da! Alright, get in the box again, we get in the box, and da! That's definitely happening to someone. They're definitely bullshit. This is happening to me every time. Every time. That's definitely happening.
Go through for the third time anyway.
How we're thinking about things, correct? But that's all based on the fact that we think we're correct.
That's right. That's right. So the thing is, there's 99 people being made who come and say, oh, I don't get shot every time. Well, that's all right.
Useful to do it
Okay, every time. So it's just a statistical
I
thing,
think
right?
that's
So
because the rails
these
by
kinds of theories
definition,
are only ever useful.
you're-
Indeed, any theory is only ever useful
but
if
you
they
have
work in the
order,
future.
and you have addition, you're going
And
to
you
get
know,
rails.
as my great
So
grand
you're
Patrick
always
Steinman
fizzling
used to
into
say,
rails
the
if
race
you
ain't
are trying
always
to order
swift,
stuff.
nor the battle to the
I'm just
strong.
trying to see if
But
there's
that's the way to be.
mathematically a better way to describe it.
Joe, does that mean we've sort of explained magic?
probably
Like if you
not.
fell through the floor,
probably
you
not
could
the
say,
thing.
well, that was unlikely.
Ah, yeah, sure. I've been thinking about it, so I'm not entirely sure, but my
Let's
suspicion
look
is
at the
that
relative probability.
rails.
Supposing I say,
Everything
I'm
is
now
very
going to
similar
turn
to the
into
rules. Yeah.
a big green
I'm
fire-eating
strong
dragon, and I
suspicion
proceed to
that
do
it's
so.
That
Which
was
do you
unlikely.
think is more likely?
There's still
That I was really lucky in a quantum mechanical tunneling event, or I slipped you acid and used some suggestion. Which is more likely?
through the ethical.
Probably more likely.
The latter is probably more, and there's a lot of possible more likely solutions that I didn't come up with right now. So in other words,
But there's
this really shouldn't affect your day-to-day lives very much, unless you think, now I'm not going to fight quantum mechanics quite so hard. You know, and maybe if that's true, then we will be able to build big quantum things. You know, we'll be able to use it for good rather than, for noise.
there is some
So,
branch of our universe where
like,
everything is
we're-
identical to Harry Potter.
Because for some reason we may have thought this lecture was going to end up at this location. We may have been talking about the Everett interpretation previously.
Yes.
And one thing that I know at least I've thought about, and I think other people sort of discussed too, is there a way that you can practically measure the difference between the Everett interpretation of many worlds and actual wave function collapse?
So I have. Okay, the short answer is for some models of wave function collapse, yes. So most people have not, in fact, invented a model of wave function collapse, so there's nothing to test. Right? If you take, say, the spontaneous collapse theories, a spontaneous collapse theory says you get enough particles together, they go ping.
Yeah.
So there's a deep fundamental decoherence process in the universe. So we'll find it somewhere. Right? Make a million things, no. Make a billion things, no. Make a trillion things, yay! All right, it's a hard experiment to sell. It's like I did a really big interference experiment. and I didn't see interference, therefore I've discovered major new physics. Right? That's hard sell. So you have to show that it scales right with number and all that kind of stuff, and that you're not just accidentally introducing some coupling that has the same scale. Okay, but technically there is a noise floor. If the Everett is right, then that won't exist all the way up. Like all the way. What can you say? Well, you can't, because everything's linear, you can't actually ever interact with another branch that's already existing. So really the hard pill to swallow there is, can I be put into a superposition? And I've just written a paper with an ASC student that explains what you can and can't do there. And the short version is, you can't deterministically, with 100% probability, know that you can be put in a superposition, but you can get pretty confident. So you can make your box, go in with a blank sheet of paper, walk in, weird stuff happens, you wake up, and your paper has, yes, you're in a superposition written on it. You put that down on the bench, you go get another piece of paper, and you go in again. And if wave function collapse is happening, so that you are not in a superposition, half the time, this piece of paper will say no. Half the time it says yes, half the time it says no. And if you are being kept in a perfect superposition, it'll always say yes. And so as the stack of paper is yes again and again and again, you can slowly become more and more convinced that yes, you're being put in a superposition. To an arbitrary degree of confidence, and what more can we ever say with a real experiment?
The only way you can determine if you're in a superposition is if you're going to.
Yes. So what this box does is it does the Joe interference experiment, it puts you in a superposition, and then brings you back together.
Yeah.
And if it measures lovely clean coherence, it gives yes. If it measures the other result, it gives no. So if you're actually having your wave function, your phase being scrambled, it gives them half and half.
Yeah.
And if you've got coherence, it gives you the yes each time. And the thing that we did in the paper was show that you can retain your memories while you do that. So obviously you can't retain your memories of being in the box in two different states. Because in order to do the interference experiment, they had to put you back, they had to put all of you into a particular state, which means they had to construct your memory. Does that make sense? Yeah. Like if you pick the whole state in order to get interference, then that person thinks a particular thing. So they can't actually have the duality of their earlier experience in it.
How can you make the measurement of interference without actually destroying your state already? Like say you went to the box, right? You determined you were in a superposition, or you determined the particle was in a superposition. So you somehow saw some sort of interference.
Yeah.
Then how are you going to reuse that same thing that was in a superposition after you actually...
So when you come out, your state is, I have a piece of paper that says yes. Right? And you can remember all the other times. You can put that piece of paper down, pick up another piece of paper that was originally separable to you, and walk back into the box and do the same thing on that system. Okay, so you have these ancillas, which are the pieces of paper which are stacking up.
So you would need to make some sort of weak measurement when you're...
You can make quite a strong measurement. You can make a perfect entanglement between the plus and minus states and your paper. Yeah.
So it is possible, like, to do this sort of experiment even with a photon, right?
Yes. Well, we do it with a photon all the time. We can show that we can put photons in superpositions all the time.
Yeah, but not the same.
Okay, so there's only one kind of detection we can do on photons that isn't destructive, and that's the Rydberg atoms in a microwave cavity detection that Hirosh does. But that's just technical, right?
Yeah.
It's because it's kind of, they move fast and they're easily absorbed. Right? We do it with spin systems all the time. Measure them and change them and flip them around. Okay. Let's talk housekeeping. So next week there's the non-assignment to play with. We'll have this just as a running tutorial. I won't have any material prepared, certainly not on that level. Historically, everyone does reasonably well on the assignments, and there's an enormous range on the exam. And so if you follow pattern, there'll be people getting 20s and 30s on the exam and people getting 100. Okay, it discriminates crazy hard. Non-assignment has those kinds of questions in it, so you can figure out where you're going to be. I would love if you all did amazing. That's my job, is to try and help you all do amazing, but I can't actually do it. Okay, and the only way to get from here to there is to practice those questions Right? I can give you help with that. I can give you more questions. If you use all the questions you want more, I can give that to you. You will have at the same time urgent, accessible things for other courses. Can I strongly warn you not to drop quantum mechanics? You need to keep it hot. You need to walk into that exam having practiced a lot. That make sense? Okay, so I tried to front load the course so that you've seen everything. It's time to see it again and again. Okay. Immediately after you hand in each assignment, you could probably have done that question in the exam. I need you to be able to do it when you sit the exam. And it's amazing how fast a brain dump can happen for a stressed person. Okay, so I need you to hit it again soon. My whole attempt at design here was to make you hit it again soon so that you actually can recall it. Sam.
Will there still be a drop-in tune on Tuesday?
Would you like a drop-in tune on Tuesday? Who's going to turn up?
There have been drop-in shoots?
Yeah, you've been
On Tuesday.
I told you this weeks ago, man.
What?
There's always been drop-in tunes.
Okay,
Yeah.
it's nice to know.
On Tuesday, Arvo. And yes, there will be another one. Okay. And also, I do spontaneous stuff, so ask me if you need to. All right, thanks everyone.